All right, now we should be live. Hello, everyone. Welcome to the ISCB Student Council's webinar series. While we give more time for people to join us, I'd like to mention a little bit about our program. So we are a small group within ISCB-SC, International Society for Computational Biology Student Council. And basically, we aim to create a platform where we can hear and discuss about exciting science from all around the world. And the way this works is we open a call for abstracts, and then the abstracts are peer-reviewed. We have already hosted some exciting webinars, and there are more scheduled over the next 2 months. And we will be hosting talks almost every Tuesday and Thursday at 4 p.m. Central Europe time. There will be a new call for abstracts in a month. So if you are interested, please follow us on social media and check our webpage, iscbsc.org webinars. So this should appear on your screen now. And this webpage also includes the schedule of the webinars. And today we have another interesting talk by Kaveesha Dilshani from Sri Lanka. If you have any questions during the webinar, please post them on chat, and I will be asking these at the end of the presentation. And thanks for submitting your work, Kaveesha. Let's hear more about gene expression analysis from you.
So can you see my screen?
Yep.
So first of all, thank you very much for giving us this opportunity for ISCB Student Council webinar series. So I'm Kaveesha here, and I'm representing the Department of Computer Engineering, University of Peradeniya, and today I'll be presenting a collaborative research of some of my department members, and so introducing our application, GeNet, which is a Python-based web application for microarray gene expression analysis. So first of all, let me introduce to you what gene expression is. So gene expression is the process in which from information encoded in a gene leads to the production of a protein. So the measurement of a gene expression level at a given time is an indication of the state of the system at that particular time. So gene expression can be measured in different ways. So microarray technology is one such method that we can use to measure gene expression. So an array is an organized array of samples. So thousands of spotted samples are immobilized in a glass slide. And so these information can be used to determine the parallel analysis of gene expression data at a given time. So by analyzing these, we can derive many useful information related to biomedical experiments, and also to derive the underlying pathogens and the underlying mechanisms related to diseases as well. So usually the data obtained from microarray technologies are contains a large number of data sets and contains noise as well. So usually the processing of microarray data and extracting useful information from microarray gene expression data requires knowledge from statistical and computational methods as well. But to derive the meaningful data, we need also the knowledge from the biological background, people with biological backgrounds as well. So there are actually some applications that are already freely available that are made for the analysis that has made the analysis of gene expression data easier, but actually we find some issues with those applications. So one of the main issues are that sometimes the user interfaces those applications use is hard to be understood by people with less knowledge related to statistical and computational methods. And also we find some applications with really attractive user interfaces, but In those cases, the performance is a bit low when compared to the other applications. And also, the analysis of the microarray gene expression data is a huge process, like it contains different steps at different levels. So, one of the main disadvantage we find with the current systems is that we have to use multiple platforms for different functions. So there are only a few number of applications where we can perform all the steps at one point. So, and also as I mentioned earlier, another disadvantage is that it requires usually like we have some customized programming languages and libraries for the analysis of micro gene expression data, but those anyway requires domain knowledge on computational and statistical methods, which should limit people from the other backgrounds to use these applications. So for that, considering these issues, to minimize these issues, we have built an application called GeNet, which was built from Python, and it's a web application. And so for now, I will show you a demonstration of that. So I hope you can see the application now. So first to use GeNet, you have to create an account, and I have already made an account. So from this home page, you can see the brief overview of what we are going to do. So you can see that some functions here are in gray color. That's because to start with GeNet, first you have to upload the file which contains raw gene expression data. Since I haven't uploaded the file yet, you cannot activate these steps now. So I'll give a brief introduction what each of these functions do. So visualization is like from this step you can visualize the patterns related to genes, each gene. So by going through the visualization step only, you can get the idea of the patterns and what are the differences with each sample. So clustering means like you can group like in genes, you know that some of the genes are correlated and some of the genes have similar features. So clustering means that you can group those genes with similar features together. And from after pre-processing step and all those, that means like, for example, you can use microarray gene expression data to extract the biomarker genes for a particular disease, for example. And then you can use those genes and you can build a different model to predict whether a person has that disease or not with a completely new data set, like in which you do not know the state yet. So this pre-processing means that like usually the raw data that you upload to the system has to be processed further to extract full information. So in pre-processing step, we deal with cleaning those data. And feature selection means, for those who are not familiar with that, in feature selection, what we usually do is like initially we have like most of the time we have a large data set with lots of number of features, so we have to reduce those features to a small count to get meaningful data. So otherwise the large sets of data won't make any sense. So we have to apply some method to get the features reduced to a count so that it makes sense. And in the analysis step, we are going to further analyze what we did in the feature selection step and the pre-processing step. And also prediction step, I think I explained earlier. And in the validation, like all these results are obtained from computational and statistical methods. So in the validation step, we can validate how biologically accurate these data are. So let me show you a small example. So for demonstration purposes, I'm using a freely accessible dataset that was obtained from NCBI Gene Expression Omnibus. So the dataset is GSC 5281 dataset, which contains 161 samples, from which 87 people are detected with Alzheimer's disease and 74 are samples of control samples. So I'll select that file as a sample file, and you can see by clicking leave, you can see how the data file looks. So in here you can see these are the sample files, and in from these 1007 SAT, these are the probe IDs. So if you take at the count, you can see that the number of features are 54,676. That means you have 54,067 probe IDs. So by looking at this data set itself, you can't, it's like really hard to get some meaningful information. So that's why we have to do some processing steps. So we'll go to the home again. And now you can see that the visualization and clustering steps have been activated because you have uploaded your file. So if you go to the visualization, you can select your file, and I select the updated file. And if you select your probe ID and see, you can see the patterns of those data related to this probe ID. And I'll again upload it. And in here, you will see the annotation table. Annotation table means, as I showed you earlier, the current file contained information of the probe ID. So these probe IDs should be mapped to gene IDs or gene symbols using an annotation table. So you can select the annotation table which is related to the dataset you upload. So for here now I'll select this, and there are also various methods that you can use for the selection method. I'm not going to explain those in detail. And let's submit. And after you submit it, now you can see that your probe IDs have been mapped into gene symbols. And you have the sample IDs, and this table gives a summary of what your data look like. So, and also in the dataset that you uploaded, these data are in different value ranges. So those data has to be like normalized first before moving further. And also, if you have noticed, like some of the data in the microarray experiments are missing. So we can't like move further with those missing values, as they might skew the results. So we have to either we have to apply some method to get rid of those missing values. So in this case, we will drop if there's any record with the missing value, and then we'll go to pre-processing. And here you can see, after mapping the probe IDs to gene symbols using probe selection methods, and after normalizing, you have reduced your feature count to 22,189. So you have reduced the dataset, which had earlier around 54,000 features, to 22,000 features. And now you can continue. So it's going to take some time to do the processing, since the feature count was around 22,186. And here you can see we have applied some statistical methods. So here the x-axis represents the fold change, and here the y-axis gives an indication of the p-value. So this fold change and p-value is used to get the genes that are significantly different. So usually we take p-value as 0.05, and if you put a fold value and calculate, you can see that the selected number of genes are in that case 1957. So if you keep on changing these values, you can see that the selected number of genes will differ. So we will go with this because this number is around 2000. So we can continue with that. So in this step, you can see like this score means and in this the x-axis refers to the number of features. So since we selected 1957, so these are the count, and you can see here from the y-axis you can see like an indication of how differently expressed they are. So you can see like after around this point 150 point that like, there's only a small increment in the changes. So only in the first 100 or 150 features you can only see you can see a significant difference. So that means that only those first first genes in those range are giving the values with significant difference. So we'll go with the 150 genes and then we'll continue. So now you can see that your pre-processing has finished, which means that your data set has been cleaned and has been minimized with gene symbols and with only the genes that show significant difference between the two samples. And here, as I mentioned earlier, feature selection means that we are going to reduce our feature count further to get only the set of genes that provide useful information. So this PCA, random forest, and extraordinary classifier are some methods that we can use to like we can use some scores based on these methods to select the best n number of features according to each method. So we can actually like change the number of features that we are going to use. So the default value is 50 and I'm going to go with 50. So what's being doing here is like it's going to select 50 features from each of these methods. So it's going to calculate 50 features from each selected method. So those 50 features are the best features according to those specified method. Okay, so now in this diagram, you can see the summary of the genes found by each method. So like we selected 50 from each, and you can see that 12 genes have been found by all the three methods. And in here, 11 means that only 11 genes have been found only by extraordinary classifier. So if you want to see what those genes are, you just have to click here and you can see the different genes, and you can also see the details of those genes processed. And if you want more details, you can also look for more details. And here, these graphs select an indication of the accuracies of what is selected here. So you can see now for this instance, so like in here the decision tree, nearest neighbor classifiers, and all those are some methods that we use to evaluate our performance. Performance means in this case we consider only the accuracy. So the accuracy is given at the highest level when we use the SVM plus linear kernel. So and in this also you can see the list of genes that are selected by each method, and you can go to analyzing step. So in analyzing step, you can see further analysis of the genes that were found by the earlier three methods. So you can see that the overlap method means the genes found by all three methods. So you can here you can see the count, and here you can see the accuracy tested with the overlap set of genes as well. And these are some further analysis on how to get the best number of genes. So for example, for different diseases and different data sets, you get around different numbers. So this gives the an indication of the optimal number of genes that could be potential biomarkers. And also, one of the main things that we paid attention to was selecting the correlation matrix, because as you know, like genes are highly correlated, and like selecting correlated genes in our final result may cause some redundancy. So we have to minimize the redundancy aspect. So for that, we are going to plot the a graph called correlation matrix, where it gives an graphical interpretation of how the genes selected by each method are correlated. So in simple terms, if the color variation is higher, that means the genes are less correlated. So in this case, we go for the set of genes with the least correlation. So by looking at these graphs, we can go with like if we select extra tree classifier, we can proceed with that in the next steps. So in that case, you can always go back and select if you like. If you feel that extra tree classifier is not the correct one, you can always go back and change your method to the other value. So these are also some analysis steps, and here you can see now we can get two set of genes, one from the overlap set that we showed earlier, and other set you can obtain by using these correlation values. So this overlap set and the correlation value, the gene set obtained from considering correlation values together will give the highest classification accuracy. So in here you can test this with different methods, and you can see that the highest accuracy here is like we are getting two co-values. So in that it select the best one to go with the next steps. So in the now in this step it gives the set of overlap features, and also the gene set that we obtain from considering about the correlation value. And in this step, it gives a further analysis of how accurate our results are. So you can so this plots gives an indication of the accuracy. So people with computation and statistical knowledge can refer to these graphs to get how accurate their built model was. And since our data set was related to Alzheimer's disease, so in this step, what we are going to do is the validation step I explained earlier. So validation is like now we have a gene set that we think is mathematically that could be mathematically could be analyzed as potential risk genes for the Alzheimer's disease. So this this file contains the genes that have been already identified by some biological sources. So what we are going to do in this step is we are going to compare our results with what is already available in these gene cards, and we can validate here. And in here also you can see the number of genes that have been found by each method, and which are like already validated by the gene cards, which contains information from biological sources. So this is a tabular form of the results. And the next step is the modeling. So in this step, we can actually use to get a completely new file. Like from here, you can submit a completely new file, and based on a model that we have built earlier, you can predict whether a given sample can be a disease sample or a sample without the disease. So like this, so each sample you can see whether the result is negative or positive. So that is basically related to the framework, and I will go to the clustering step as well. So in clustering means, as I told earlier, it also gives a visual interpretation of how each gene is correlated with others. So we can select a file and submit here. So it will generate clusters. So clusters means like in here you can see the number of clusters is known as 25. So altogether there are 25, and by selecting this you can like these are like IDs. So you can select. So if we get an example, and now you can like see how each one is interrelated with each other. And if you weave again all the 25 clusters, it will give a weave like this. So for anyone who needs more information about this, you can refer to our user guide as well. So we have a user guide made for this. So for anyone who just want to play with the application and just want to use it without going into deeper details, you can use the user guide. So it gives step-by-step instructions on how to use the application. And for those who want to understand what's really going on behind the frame and want to get a deeper knowledge, can refer to our manual. And also you can go for a report. So by using this report, you can download some results with each step. So after performing these steps, you can download this report to get a summary of the results that you have obtained. So that's with the demonstration, and for more information, as I told earlier, you can use our web page with the user guide and the manual. And also we have an official YouTube channel that provides some crash course on how to use this application. So you can also refer to that. And so that's all about our demonstration. And as I told earlier, so this was a collaborative effort of the Department of Computer Engineering of University of Peradeniya. So the contributors were Shehan, Perera, Kaveesha, Chamara, Gunarathne, who are currently undergraduates of the department. And this was done with the supervision and guidance of Dr. Daman, Dr. Rajita Navaratne, and Professor Roshan Raghal of the same department. So that's all for the presentation. Thank you. And if you have any questions, you can go ahead.
Okay, thank you, Kaveesha, for this very interesting and very clear presentation. It looks very easy to use, to be honest, and Also, I think this was one of the very few cases where a live demo worked. So thank you. There are already some questions in the chat box. I will be going through them, and if you have more questions, please post now. So the first question is about the different platforms and techniques for microarray. Since there are different platforms, would your normalization method bias towards certain, I don't know, would include some biases, or can you apply the same normalization technique to all platforms?
Yes, so actually the normalization, for now, we have only used one normalization technique, but it should be different. Like in the further improvements, like we have to, it always depends with the data set. So we have to normalize it according to the data set. So like 80% of our effort should be going in the pre-processing step. So rather than in the analyzing step, so we have to focus more on the normalizing step. So for now, at the moment, since this is still in the developing stage, we are using an inbuilt library from Python to do the normalization. And also like there are like various researchers and various like different researchers specified only for the normalization of microarray gene expression data. So that those things actually should be added to the application as well. Like it would improve the accuracy and performance. For now, we are only using an inbuilt library.
Okay, thank you. And there is another question about the functional interpretation of the results. You've already covered that a little bit. But for example, I can also add my question here. So you also showed the validation step with external data, but I didn't really quite get where that external data is coming from. Is it from a database or?
Yes, actually, that's from a database. So that was from www.genecards.org, as I can remember. So there's a different platform for gene cards where they have like different data related to different diseases. So since I used a data set related to Alzheimer's disease, I only integrated with that. So, but also you can use that same website for the interpretation of other diseases as well. And also, like we have in that application, also we have a function where you can upload a file. So if you already know the data or already identified genes which are already biologically validated by some other source, you can also like put them in that format and upload it to the web application. So currently we only have some default files. So if you want a different file, you can always upload it and check the validity.
Sounds great. And I also have another question. So this is mainly just aiming at microarray analysis. I was wondering if you have any plans for RNA-seq data as well to have something similar.
Yes, actually, we had we tested this application with the people with biological background and we received some feedbacks as well. So one of the main suggestions was to improve this to use with the other kind of data like sequencing data and all that. So currently this can only be applied to microarray technology because we have focused only on that aspect. But in the further steps, this application could be improved to use the other data as well.
Yeah, it looks very useful actually and helpful for biologists in general. All right, I cannot see any other questions. I hope I'm not missing anything. So maybe we can close now. Okay, yeah, there's no other question. There are a lot of comments like this was a really nice and helpful tutorial. Yeah, there are nice comments.
Yeah, thank
All
you.
right, thank you very much for this nice talk, Kaveesha. And thank you all for attending. So we will have our next webinar next week. So hope to see you all again next week. Bye.